presses by accident, it just blocks it out. But just press it. One second. Yeah, go ahead and get started. Okay. Hello, everyone. I'm Milinda, and I'm going to talk about DandroGR. It's another numerical relativity framework, and I'm basically going to talk about the GPU acceleration of the DandroGR framework, and this is a collaborative work with many collaborators, and I'm just presenting our work here. So first, the question is, do we really need to use GPUs, or is it efficient to use GPUs for simulating binary black hole spacetimes? So if you look at most of the computing resources, so if you look at the top 500 list, all the supercomputers that we have, they are increasingly become more heterogeneous. So they have accelerator units, so it's better if we can use them in efficient way. And also they become more complex to program and to get good performance. And we have a lot of fine-grained parallelism. And also, I think everyone here knows better than me about the role in numerical relativity in the gravitational data analysis. And the key thing is we need numerical relativity to tune all these other surrogate models. And the main point is numerical relativity is very expensive. Some simulations can take from weeks to months, and we need thousands of waveforms to build these surrogate models. So anything that we can do to speed up these computations can be beneficial. So the main question is, can we use GPUs for doing GR simulations? So there are two main challenges if you are familiar with GPUs. So normally GPUs are good at doing data level parallel tasks, so single instruction data level, multiple data. But there are two main challenges to using GPUs for GR simulations. One is we have adaptive refinement, and this can trigger this unstructured memory accesses, which is not the most suitable memory accesses for GPUs. And also, these are going to be memory-bound computations. So I think these are some of the challenges that we all face in numerical relativity. So the first is the underlying equations are complicated. So if you are just evolving the vacuum Einstein equations, in the BSSN formulation, you have 24 degrees of freedom. And if you go to other formulations, you might have more degrees of freedom. And also, we need to have long time horizon simulations. And these computations are memory bound. And also, we have to use a AMR, adaptive mesh refinement, to capture the in our simulations. So the other challenge is the doing large mass ratio simulations, binary simulations. So I've here put the mass ratio of the binary and the reasonable resolution requirements to keep for the smaller black hole and the larger black hole. And if you are approximating, if you're starting from not a large separation distance, so if you're starting from 8 AM separation distance, these are the time to merger, and then these are the number of time steps. So you can see when the mass ratio increases, and since we are using explicit time integrators, our time step size is limited by the spatial resolution. And so basically, when you go to large mass ratios, our mesh size increases and our time step size decreases. So this is why this is a grand challenge in numerical relativity. So for the purpose of this talk, for the results that I present, and we use this BSSN formulation of the Einstein equations. So it's 24 coupled nonlinear hyperbolic PDEs, and we have 4 constraint equations, and we use free evolution. So we just start with our initial condition, initial data, and we start evolving these 24 equations, and we do this constraint monitoring. So in this presentation, I'm going to mainly focus on extending our Dandre-GR framework to support the GPU acceleration for evolving performing binary black hole simulations. And so we are interested in doing binary black hole simulations, and we use adaptive octaves for our spatial discretization. And we use 6th order finite differences in space and explicit RK4 in time. So a little bit about the Dandre-GR framework, how we are, there are many frameworks. So of course, the Einstein toolkit, the spectra code, and other existing codes. So these are some of the things that we want to highlight in the Dandre-GR framework. So we use octaves for our spatial discretization, and using octaves with this, I will explain what we mean by this wavelet transform. We can get localized adaptivity, where we don't have to specify a hierarchy of grids. Instead of that, the refinement is automatically guided by the wavelet transform, the wavelet coefficients, which I will explain in more detail. And also we have this symbolic code generation framework that supports hardware-specific code generation. So if you generate a code, for example, especially for evaluating the Einstein equations, the code that is generated for the CPU might not be the best code that executes on the GPU. So we do support hardware-specific optimizations during our code generation, and all the load balancing and partitioning handled by the Dandre-GR framework. And we use this space fitting curve-based partitioning scheme, and it does support both CPU and the GPU evolution. So you can run Dandre-GR on the CPU cluster or GPU cluster. And actually, this is it's not really limited for numerical relativity. So in using Dandre-GR or Dandre framework, you can do any time-input system with finite difference with explicit time stepping, to use both CPUs and GPUs. And in terms of scalability of our software framework, we have shown good scalability across more than 200,000 cores in the front of the computer, and all our codes are open source available. So basically, this is Dandre 5, which is octave-based PDE solver. it's not nothing to do with relativity, and it does support both finite difference and finite element discretizations. And this is basically the special case of Dendro, which is basically using for doing relativity simulations. So if you're not familiar with octrees, the octrees are widely used in many other domains of computational science. So I have shown example of 2D example. So octrees naturally arise if you use a 2D domain. If you hierarchically split each axis, you will get each non-leaf node get 4 children in 2D, and if you do it in 3D, you will get 8 children. And you can for each of the subdomain, you can hierarchically split again. So basically, you can refine until a particular maximum depth. And when we are storing the nice thing about octrees is when we are storing this grid structure, we can only store the leaf nodes of this tree. Basically, if you want to know about the non-leaf nodes, which is in this purple color, so you can do like a bottom-up traversal of your octree. So this is one of the main reasons the octrees are widely popular for handling the spatial discretization as a data structure. And you can come up with clever algorithms to manipulate this data structure to get efficient AMR schemes. So, in this example, this is an actual simulation that we did using DataGR, and you can see how these octrees get automatically refined to capture the propagating wave, the wave. So this is, like I said, we don't specify like a priori decision about where to refine. Instead of we specify a wavelet tolerance. So how we guide our refinement is basically using this wavelet adaptive multi-resolution. So what we do is basically the wavelet does is basically it kind of computes the sparse representation of a given function. So basically, you can represent a given function in the V naught space or V1, V2, V3, where we increase the resolution on these V spaces. So the wavelet basically computes the error that occur if you want to construct let's say the V3 solution at the V3 from the V2 information. The information on the V2 grid, if you want to construct information on the V3 grid, what kind of error that you make. If that error exceeds some specified tolerance, that means we need to keep this V3 level. Otherwise, we can get rid of this V3 level. And basically, if we needed this V3 level, we can reconstruct from the V2 level. So that's the basic idea of the wavelet refinement. So basically, all you need is how much error that you can tolerate. So this is what we refer as the wavelet tolerance. So it can be a spatially dependent tolerance function, and then we generate our initial grids with this which satisfy this wavelet refinement criteria. And when we evolve it, wavelets automatically do the refinement for you. So this is just to show you what kind of grid structures that we get. So this is one of the simulations that we did for Q equals mass ratio 1:16. And if you zoom in, you can see I'm zooming in close to the smaller black hole. You can see how our grid structure, and this is automatically handled by the wavelets. And this is the finest resolution. I think this is the finest resolution that capturing the small black hole. So a little bit about the Dandro. So basically, because you have this arbitrary adaptivity, you need to and we are a distributed memory form, so you need to handle the all this mesh partitioning, construction, all this stuff is done using this space filling flow-based partitioning method. So instead of using graph partitioners, which is more accurate in terms of balancing communication cost and encoding the communication cost, but they are also more expensive. So we have this efficient space filling flow-based partitioning scheme that tries to also balance the workload and also tries to balance the communication cost as well. So before I get started on the GPU acceleration, I think it's important to identify this notion. So some notation. So what we call an octant is basically a cell or the leaf node in our octree that is called an octant. And each octant is placed with the uniformly spaced R cube grid points. And a patch is basically octant with this the padding region, which is needed to evaluate these finite difference stencils. So basically, for sixth order, for basically for each patch, which contains k points in all directions. So basically, the patch will be R plus 2k cube. And for all the simulations presented, we use R7 and also K3 because we are doing sixth order finite difference in space. So and as I mentioned, we use finite differencing to evaluate the spatial derivatives. So how we do that in the octree grids. So basically, this is our octree representation of our underlying fields where I have placed the grid points. And basically, what we need is we need to, in order to evaluate the derivatives, we need to go from this octree representation to this patch representation where we have done this padding correctly. With if we have a coarser region next to us, we would have to do interpolation. If we have a finer region, we would have to do sorry, if we have a coarser region, we have to do an injection. If you have a finer region, we have to do an interpolation. So this is what I refer to as this octant to patch representation. And then once this is the representation that we evaluate our derivatives. So once the derivatives are evaluated, we go back to this the patch representation. So basically, the numerical any numerical relativity code boils down to the evolution boils down to this algorithm. So basically, we have a whatever state at t equals t0, and we want to evolve this system forward in time, and then basically we since we have AMR for a given re-grid frequency, we have to change our grid to adapt the to capture the varying solution. And in our GPU acceleration, these parts have the construction of the mesh and partitioning of the mesh happens on the host. So what we are trying to do is to use these so once we construct a grid for FR time steps, we are trying to use GPUs to accelerate our time integration. So we have basically I've highlighted in red what the computations that executes on the device or the GPU. So basically we have this octant to patch. Basically the process I described, going from the octant representation to going to patch representation, and then we would have to evaluate the right hand side of our the PDE system, and then once the right hand side is evaluated, we again switch back to the patched representation, and then we go to the next update. So this is basically the key computation. So the red computations, so if you are evolving in the CPU, you can use the CPU to do these computations. But in this presentation, I'm going to focus on how to do this. Is there an efficient way to do these computations in the GPU? And some of the challenges related to that. So actually, when we were writing our GPU code, we realized some of the inefficiencies that we had in our CPU code. So I would want to highlight some of the some optimizations that we did to our CPU code while we trying to design our algorithms for the GPU. So basically, if you want to compute this patch representation, you have kind of two main approach. So basically, you can either loop over the loop over patches and gather the information. So basically, if you want to compute the patch A, you can gather information from every neighboring octant, and this will give you scattered reads, because because we can use adaptive reads. The nodes of each element is not going to sit contiguously in the memory, and also these required interpolations or injections are going to be duplicated between the neighboring patches. And the other approach is basically we loop over the octant, and this will for a given cell, most of its node going to be have more contiguously, so you will get uniform reads. And also the most important thing is the octant information is reused between multiple patches. So this is and also it doesn't have redundant interpolations. So this is what we found for the GPU. What we found looping over the octant and that scatter its information for required patches is more efficient. So then we did an experiment, basically comparing the two approaches for number of octants and also the time per octant to do this octant to patch computation. And you can clearly see the looping over octant is faster, filling these buffer zones than looping over patch computation. So in the GPU memory, the octant to patch, this is how the data movement happens in the GPU memory. So if you're so basically in GPU, you will have the global memory and the shared memory. And once you load something from the global memory to shared memory, you can get higher performance. The better more reuse you have the data in the shared memory. So since we are looping over the octant approach, for each octant, we use these generated maps to get data from the global memory. So basically, we gather the octant nodes to the shared memory, and then we have these workspace variables to do the interpolate or inject. And once the interpolation and inject is performed, we write things back to the shared memory, which is from the shared memory to the global memory, which is the same element with the appropriate padding regions. So that's so basically that's how we implemented the Oden to patch computation, and this is now I'm going to talk about how to evaluate the right hand side, which is using our symbolic code generation framework called the SymPy-GR. So I've shown here the BSSN equations and how these equations are written in the SymPy-GR. So why we have some symbolic code generation framework? So I think everyone here knows the equations that we are trying to compute. If you want to write code by hand, it's harder to implement. You can easily introduce errors, and it's also very hard to optimize. So basically, the idea of this symbolic code generation is basically you have whatever the governing equations, either relativity or fluid dynamics or whatever the physics you want to do. And basically, you have the SymPy module, which basically can do these symbolic manipulations, and also some differential geometry module, which supports some of the derivative evaluation that is needed for GR. And basically, the important for the optimization part, important thing is basically can do this expression to expression transformation that basically kind of generate code suited for different architectures. And basically, then we have underlying architectures or the programming languages that we want to spit out code. So, how do we do this architecture-specific code generation? So basically, we using the SymPy-GR framework. What we really care about is the expression tree of the evaluation. So once you get the expression tree, this is kind of the ultimate abstraction of the computation for the right-hand side you want to evaluate. And basically, depending on the architecture, you can do different transformations suited for different architectures. So that's how this symbolic code generation framework kind of abstract out basically generating performance optimized code for different architectures. So actually, so the right-hand side evaluation on the for the Einstein equations, and also either for the CPU or for the GPU, is not that trivial. What's the most performant way to do that? Basically, for the right-hand side, basically you have two parts. Basically, the first part is you need to evaluate all the derivative computations that is required for this Einstein equation. So basically, you have roughly application of 210 derivative applications for each stencil point. And also, once you have computed all these derivative variables, you have to compute, assemble these derivatives in some algebraic way that is given by the equation. For example, you have the evolution of the Lux function, which is given here. Basically, you need to know the derivatives of the variable alpha, x, y, z derivatives, and then once you compute the derivatives, you just assemble it in this way. So that's why what I mean by the derivative computation part D and the algebraic part A. So for the right-hand side evaluation, basically you can do an unfused evaluation. What I mean by unfused is basically you compute all the derivatives and store the derivatives in the memory. So basically, at the stage one, you compute and store all the derivatives, and stage two, you do the algebraic evaluation. I think this is if someone is implementing it, seems naive way of doing things, but then you can do a fused evaluation. So basically, you evaluate the derivatives, and you don't store those in you try to compute the instead of storing writing that back into a memory location, you try to use that derivative information to compute the right hand side of a particular equation. So if you consider like a infinite cache model for that's an abstract machine, and then basically if you compute the arithmetic intensity, that is what matters if you want to get good performance. So there's the fused evaluation has an arithmetic intensity of roughly 6.6, and if you split this into two stages, the unfused evaluation, it has a low arithmetic intensity. So if you have a low arithmetic intensity, it's hard to get performance. For you're mainly going to be bounded by the memory. So it's, because of that, I think either CPU or GPU, when you are evaluating the Einstein equations, I think the fused evaluation should give you better performance. Hence, faster compute time. So because ultimately evolving Einstein equation boils down to how fast you can evaluate the right hand side of the PDEs. So this is the roofline roofline performance model for the right hand side. So if you are not familiar with basically the roofline performance model, basically the x-axis is basically have the operational intensity, which basically tells you the ratio of floating point operations that you do for access of 1 byte of data.
Sorry to interrupt. So we're now in the coffee break time. How many more slides do you think you have?
I have, I don't know, I think another 10 slides, 15 slides, I think, yeah.
Oh, never mind, sorry.
Yeah, because it's 2 to 3, right?
Yes.
Yeah. So basically, if you have the operational intensity and the y-axis is the performance that you can get. So these solid lines basically have the peak performance that you can get in this architecture. Basically, this is the empirical performance on the I think this is for the A100 GPU. So basically, you can get 5 teraflops of peak performance. But this is the performance that we could get actually when we are trying to evaluate the right-hand side on this GPU. So this is the observed on the right-hand side performance. So if you look at the previous slide, I had the theoretical operational intensity of 6.6. Basically, it tells you if you have that arithmetic intensity, you can you should be able to hit the peak performance of the GPU. So, but this is the performance that we could hit. So there's something clearly is missing in our implementation. So the main reason for this suboptimal right-hand side performance is basically we have high register pressure. Basically, this is even though we have our BSSN right-hand side is 24 inputs to 24 outputs computation, we have to compute these 210 intermediate derivatives and all these tensor dependencies. So basically, the next question is basically how can we reduce this register pressure to get better performance. So for the right-hand side evaluation, we kind of did 3 strategies for the code generation. So the earlier in the previous works of Dan GR, we proposed this SimPy-GR plus the common sub-expression elimination. Basically, we try to reduce the number of evaluations that we have to do, and these are basically we have. In this approach, we get 900 thread local variables, which kind of magnifies the register spilling. So normally in a CUDA architecture, you can, I think the maximum number of registers you can use is 255. But if you use all the registers that is allocated for the thread, then it will reduce the GPU occupancy, which leads to bad performance. And so then we thought about how to do this binary reduce approach. So basically, we rewrite expressions as binary reduce operations, because ideally the compiler should be able to do that. But for these large expressions, I don't think the compiler will do these optimizations. And so with that, we were able to go from 900 trade local variables to 675 local variables. Still, we are over the maximum number of registers allowed. And then we did try to look at the equations. This is like manually staging, but trying to come up or trying to reorder the equations in a way that will reduce the live range of these temporary variables. So basically, once a temporary variable becomes dead, the compiler can reuse it for another computation. So basically, the idea of the staging and doing the common sub expression elimination is
10 minutes.
Basically, we have the alpha derivatives. If you compute the alpha derivatives, and we try to compute the right-hand side of the alpha derivatives and be done with the alpha derivative computations. So, the idea of the binary reduce approach is basically we look at the computational graph, and any topological sort of this computational graph is a valid order of traversal of this graph. So hence, it will generate a correct code. So we, as a heuristic, we use this topological sort of the line graph of G, the computational graph, and try to generate the code for the right-hand side. So this is what we known as the binary reduce approach, and comparing the three approaches. So if you use the SimPy-GR with you are trying to do try to minimize the computation by reducing the common sub-expression elimination. These are basically the compiler, the spill stores and spill load. So basically, these are indicating the register spills. So basically, if you do a binary reduce approach, you can reduce the spill stores and loads and stores, and you can see if once you reduce these the register spilling, you can get a 1.5 file speed up, and by doing this staging also, we can get a close to 1.7 speed up. So I think for the main challenge for evaluating the Einstein equations on the GPU is allocating registers. I think this is for how to efficiently do this. I think it's still suboptimal. So there's no maybe we can come up with a better strategy, which reduce the spill stores and loads, which will give us a better performance. So this is basically the rootline analysis of the other computations. Basically, is octant patch representation, which we get around 1,000 gigaflops, 1 teraflop, and for the right-hand side also we get like close to 1,000 gigaflops. So roughly we get like 1/5 of the GPU peak performance. So for the experimental setup, we did our code performance evaluation for CPU runs. We did on the frontiers of the computer. For GPU runs, we did the Lone Star 6 supercomputer. So for all the CPU GPU comparisons, we did a node-to-node comparison. So we compared a full node of the Lone Star 6, which has 2 CPUs. To a single, basically 2 CPU sockets, to a single NVIDIA A100 GPU. So basically, these are time per octant, if you want to evaluate the right-hand side using CPUs versus GPUs, so you can see we get roughly 2 to 2.5 speed up, and this is basically all the stages in a time step. This is octant batch computation. This is the blue bar. The blue part is the MPA communication. The purple one, the right-hand side evaluation, and this is patch to octant representation. So this is the shaded ones are they're doing using the GPU implementation. And this is comparing the single CPU node, which has 2 sockets, versus single GPU. And this is basically the strong scalabilities. We did, this is the Lone Star is not like a large GPU cluster. We could go up to 16 GPUs, the maximum that we could use in that cluster. And this is the time zone for 5 RS time steps, and these are the parallel efficiencies of the strong scaling study. For the weak scalability, since we found some of the inefficiencies that we had for our CPU code, we eliminate those and improve our CPU code as well. And this is for doing actual for like a evolving the BSSN equations. I mean, for actual production runs, you don't need to go up to this many cores, but this is just to test the scalability of our framework. So we show that we can scale up across to, I think,
5 minutes, please conclude.
Half of the Frontera machine that did this scalability study. So, and also we did compute the actual gravitational waves using our GPU accelerated tangent solver, and basically I'm just plotting here the just like a verification comparing the CPU versus GPU, because we did a lot of this optimization for the right hand side. We wanted to make sure that we are computing the correct right hand side. Also, there's nothing wrong in our implementation. So basically, the CPU waveforms are kind of verified with the last zip code. So we basically comparing the tangent CPU versus tangent GPU. So I think does it? So these are the actual production runtimes for mass ratios 1 to 8. And these are the resolutions that we did, and these are all these simulations are starting from 8 M initial separation distance, and this is the final time horizon that we evolved, and this is the overall whole time. This is including all the input, output, I/O terms, and all this. This is for like production terms. So in conclusions, I think. This is at the time, I think this was done in 2023, I think, if I remember correctly. At the time, this is for the best of our knowledge, this was the first time we used GPUs to accelerate binary black hole simulations. And so using GPUs, we can, comparing 2 CPU sockets to a single GPU, we were getting like 2 to 2.5. I mean, these are memory bound computations, so the maximum speed up that you can get is limited by the bandwidth of the CPU versus bandwidth of the GPU. And also wanted to highlight the sparse adaptive computations on GPUs. It's challenging, but you careful consideration of algorithms, I think you can do it. And the main thing, I think, evaluating the Einstein equation right-hand side creates a lot of register spinning in the GPUs. I'm pretty sure this happens in the CPU as well, but probably nobody cares. But this degrades the performance. And also you can find all this code is available on our the repository. And finally, I want to conclude my presentation with these acknowledgements for our funding resources. And if you want to
2 minutes.
This is the main paper that describes about accelerating the tangent GRVs in GPUs, and also I've listed some other papers if you're interested in how to knowing how things work in that area. Thank you.
So I'm going to selfishly ask a question first. I don't fully understand the connection of the octree with the wavelets. So do the wavelets drive the octree refinement, or is it that, or is the refinement entirely independent from the octree?
Refinement is octrees can have any refinement. So wavelets is the one that drives the octree refinement.
Okay.
Yeah.
So follow-up question there. On a given
1 minute, please conclude.
you called it an octant. Are the within an octant are all the cells populated?
Octant is like that's the smallest unit in our grid. The octant is the smallest unit.
Right. So an octant is, say, you said it was like R cubed cells.
R cube points, yeah.
Are all of those points active?
Yes.
Okay.
Yeah.
Right, let's move on to audience questions. Go on, you raise your hand first.
Okay. I also have questions about the octree, but a little bit different. So for the GPUs, you're using the shared memory on the GPU to store the octree when you do decomposition. Do the math. If I have an octree, 7 points in there, cube doubles, then I use 2 kilobytes of memory. So,
Octree, octree is not used in the shared memory. Octree is stored. Octree maps are stored in the global memory.
right. Okay. The data that was on the octree that you're using to fill in the patches.
Yes.
That you copy to shared memory.
Yes.
Okay, so that's 2 kilobytes.
Yes.
Is that a big of a lot of limitation for you that you're running out of shared memory? That already variable.
I think in the shared memory you can store. You have. I mean, I don't remember exactly, but you have more shared memory than 2 kilobytes, right, in the GPU. Yes. So basically, but I think storing those is important because we have to we kind of have to store those because we have to do the interpolations. Otherwise, if you are accessing the octant nodes again and again from the global memory, the buffer, this filling the buffer zones code will perform horribly on the GPU. So I think the running out of shared memory, probably we use a little bit more shared memory and can reduce the GPU occupancy. But I think but we cannot avoid it. I mean, because accessing things from the global memory is going to be less performant than that. I'm pretty sure.
Questions? All right. Well, I'll ask more questions. I have more questions. So going back to this octant versus patch differentiation that you made. Is there a reason why you don't just keep around ghost zones and do ghost zone synchronization?
The ghost zone synchronization happens on the octant representation.
But I mean, why do you have two representations?
Because we want to evaluate finite difference stencils. Otherwise, we have these refinement boundaries that are not matching resolution.
Yes, but I mean, a typical strategy that people use is they would have, say, a single reference point. For example, how Carpet works multi-patch is that you have a single octant, as you call it, where you always have a patch where you keep track of which of your zones are your interior and which of your ghosts, and periodically you fill your ghosts via interpolation.
Yes.
Is that what you do, but you just describe it differently, or do you do something different?
No, I think that's what we do. So basically, we have the octants, and when we want to compute the derivatives, we fill the padded zones, and then evaluate the derivatives, and then once the derivatives are evaluated, I think the patch representation is redundant.
Okay.
Yeah.
So you're making this okay. So it's basically the same. You have a
yes.
Like when you were describing octant to patch to octant, you were really describing their scale exchange.
Yeah. Okay. What do you mean by halo exchange between the partitions or between the neighboring cells? Yes, it's information exchange between the neighboring cells. Yes.
Did you, related question, on the GPU side, you see it, did you look at performance as a function of size of your octants?
I did not look at the size of my octant. Like you mean the number of the width, the halo region width, right? You are asking.
No, I'm asking about the interior region, so R cube.
Okay. I haven't looked changing the R cube size.
Performance should change. I mean, there's an optimal choice perhaps in CPU. That optimal choice might be different. Performance might change very dramatically.
Yeah, but yes, so yes, that is true. But we decided, because I mean, since we are decided to move with the sixth order finite difference, I mean, changing the R cube size will basically, you can pack more points and still evaluate the sixth order derivatives, but I think it's kind of like not required to do. It's
Well, I mean, what size do you use?
right now it's R is equal to 7 points. For
Your
seven,
most halo is 3.
yes. So it's a 13 cube. The patch will be 13 cube.
Really tiny. Probably get massive performance gains. AMR.
Yeah, maybe. Yeah, I would have to see that. Yeah, but yeah, I think the right now the performance is, I think the main bottleneck is how to evaluate the right hand side. I think that the register skills really kills the performance. Yes.
Since you talk about the register skills, so we are first trying to also get the code to work on GPUs, complex memory projects, and we are also not register skills. Worse, I guess, in the sense that we're going to be using Cactus, where every variable that you're using comes as a Cactus pointer, it needs to be registers. So that makes it worse. Do you have any other tricks that you've tried to reduce the register usage other than what you've shown there? I mean, 56 registers per thread is tiny.
Yeah.
24 variables.
I think the methods I've shown you here, I think they kind of does not solve the problem entirely. I think the proper way to do is you build the entire computational graph for the right hand side evaluation, and you have to do some way of partitioning of the graph that reduces the register spills, as also it reduces, because when you do a partitioning of the graph, then you have to do a redundant reads if you want to read again. So there has to be some way a balance between you make a partitioning of the graph that reduces the spills, also reduces the redundant computations. I think that would perform well, but we don't have a code to do that right now. I mean, yeah, I think that's the correct way to address that problem.
I'll ask one final question. I don't see any more. Talking about the symbolic algebra optimizing this graph. So every valid graph you pick that you can is a valid expression of the equations.
Yes.
But numerically they may be different, right? Because floating point numbers are not associated.
Yes.
More like generically with computer algebra package code, this is probably or it's have you thought about how to if you decide to change that representation, how to compare across iterations with floating point roundup?
Right now, we consider any topological sort of the graph is a valid traversal order without considering this numerical instability issues. But I think right now in our framework, we don't consider it. I mean, we just generate a code and run it and see if it creates any problems or things like that. But in our framework, we don't have we don't check if this approach is more numerically stable than different traversal. Yeah. I think that's kind of a limitation that we have, right? But I think most topological sorts in this graph, that at least I tried, seems to be work without any problem.
Yeah, I'm not saying that you'll have like numerical issues in the sense. I was more thinking about like for the purposes of validation of two iterations of my code, I ran different numericals. So it looked like I generated different equations out of my algorithm. Then it's not possible to compare between versions. Again,
Yeah.
so it's more of a like a debugging thing.
Okay. Yeah.
Human workflow.
Okay. Yeah, I think right now what we do is basically we generate a code and we just compare with the RHS code that we trust and compare the relative errors of all the fields that we compute. Is it for the same initial data, same input data is the same? Do we produce the same? It should match close to the machine precision. The relative errors.
More questions? In chat?
No.
All right. Well, in that case, thanks very much.
Okay.